Right, so you should be able to see the slides now. Does that work?
Yes.
Okay.
Yes.
Yes.
Okay, thank you very much. It's also great to hear from from people in the room, just to know that I'm not speaking to no one. Great, so thank you very much for the introduction. I could only follow the English part myself. I couldn't quite follow the Portuguese part, but I'm quite sure that they were probably the same thing that you said. Thank you very much for the kind introductions and for summarizing Stefan's and my work as well. So for this workshop today, we're going to do it such that I sort of start with the first bits, and then Stefan takes over at some point. Just as a disclaimer, he's also really good at the technical bits, so he's going to explain some of the details about the methods and how they can be used and sort of also programmed. So if you have any questions about the details, then probably Stefan will be the person to answer some of those. But yeah, we will start with some more general points, just explaining the methods that we want to present to you today. So yeah, our topics today is Snowclones. Maybe not all of you are familiar what those are. They're specific kind of constructions, and we hope that sort of we can show you some examples of those today, and then suggest to you some means of how those Snowclones can be analyzed with corpus methods. So as a brief outline for what we're doing today, first we would like to introduce what Snowclones are. And Snowclones are a type of partially filled constructions. So there are other kinds of partially filled constructions in language as well. So we will also talk about those just in case that someone is not only interested in Snowclones, but also in other constructions. Many of the methods we talk about here can also be used for other constructions. Then we will talk about the first part of the methods we want to discuss. This is called a structural analysis. So there are several methods that are part of this. Then we will talk about the second part of these methods. And here we're focusing on semantic vector space analysis. So that's our second big focus for today. And then at the end, we will sort of summarize and talk some more about implications for corpus-based research. So in terms of the goals of this short course, we thought we would try to aim at 3 goals today. So at the end of the short course, you should be able to have some knowledge of what Snowclones and other partially filled constructions are and how they can be investigated with the help of corpora. You will also understand the basic ideas of 2 corpus methods, called structural analysis and semantic vector space analysis. And finally, you will be familiar with some tools for implementing these methods in the R software environment. So Stefan is going to give a few examples of how those methods can be used when you've downloaded the R software, which is one of the most commonly softwares in statistical analysis and in corpus analysis. Just as a brief note at the beginning, questions are very welcome. So as Marcia just outlined, we are very happy to take questions in English or in Portuguese with translation, if someone could help us. So please just write them in the chat at any point during the session. And especially since there's 2 of us, one of us can always have a look at the chat while the other person is talking. Please don't be shy. We're very happy to answer any question. If you want some more explanation of a concept, or if we were like going a bit fast at some point, you could always just write that in the chat and we would explain it more. Or if you want to know more about a certain topic, we can discuss it a bit further. Also, in our presentation, we have included a few discussion questions today. They are relatively open-ended questions where we're just wondering if you have any ideas about these topics, or if you can think of any other examples that also fit into this topic. So we would encourage you that when we raise these questions, and there's this like red question mark on the slide, that you have a think about them and maybe type in the response into the chat, or if you want to unmute yourself and also contribute something, that would also be great. So again, like, don't be afraid of saying something that could be wrong, because it's quite a small workshop. So we can definitely discuss whatever ideas you come up with. Right, so that's sort of for the introduction. Let's jump into the topic. So what are Snowclones and what are other partially filled constructions? So we wanted to start with some examples of Snowclones. One of the examples we're going to focus on today is the mother of all X. So you might have heard expressions like these before, like the mother of all battles. So when you talk about a particularly intense or big or a scary battle, you could call it, you could say it's the mother of all battles. Or if you're talking about a gigantic traffic jam, you could say it's the mother of all traffic jams. And same for hangovers. They could be, if someone has a hangover, a particularly big one or a particularly bad one, it could be the mother of all hangovers. And together, these examples illustrate a pattern, which we can describe as the mother of all X, where X stands for any noun that fits into this pattern. So this is an example of a snow clone. Another snow clone is X is the new Y. So you might have also heard expressions like pink is the new black, which sort of means pink is now the sort of the fashion, where black before used to be the fashion or the fashionable term. So where one concept replaces the other one and becomes more modern or more topical or more interesting. Or for example, when people say stats is the new grammar. So instead of doing grammatical analysis, if people focus a lot on statistical analysis, they might put that in the form of the snow clone. So that's the second example we're going to focus on today. There are a lot more snow clones. For example, another snow clone would be in space, no one can hear you, and then you can insert a verb phrase. For example, in space, no one can hear you scream. So this snow clone actually derives from a film title, I think. So that's the original quotation, in space, no one can hear you scream. But then when that becomes a snow clone, people have started inserting other verbs or other verb phrases into this open slot of the snow clone. So now you have also other examples. This expression gets reused to say things like in space, no one can hear you groan, or in space, no one can hear you sing in the shower. So you can also put entire verb phrases into this construction. And then finally, we also have snow clones which use more multimodal means. So here you can see it's actually not a word which is used in snow clone, but actually a symbol. And you know probably lots of examples of this snow clone, like I love New York, or I love Rio. And also what's quite interesting with this snow clone is that you can extend it even further. So this example is a bit more complex, which is I, then you have this symbol for shamrock, and then you have a beer glass. And I'm not sure if you can see it, but it says Guinness on the beer glass. So this is it's a point about Irish culture. So Guinness is a typical beer in Ireland, and the shamrock is also typically associated with Ireland. So here someone has used this construction in a creative way to extend it, and it probably means something like I love New York in the same way that I shamrock or I love Guinness. Cool. So these are some examples. How could we define snow clones based on that? So one definition that has been suggested by Traugott and Trousdale is that snow clones are schemas. So they are some kind of abstract pattern that grow from relatively fixed microconstructions that are usually formulae or cliches. So all these expressions that we saw before, they usually they derive from a specific origin. For example, the in space, no one can hear you scream. And then they have a sort of like a prototypical meaning associated to them. And they're almost like a cliche sometimes, a bit like something is the new something. Like that's a bit of like a recurring expression that gets used again and again. In case you're wondering about why these things are called snow clones, this term actually comes from a specific example. So when snow clones were first discussed, it was actually in a blog entry. So on the blog language log, Jeff Pullum talked about these expressions. And he used the example of if Eskimos have N words for snow, X have M words for Y. So there's a common cliche that Eskimos have a lot of words for snow. And people have started adapting this kind of cliche in order to make a snow clone out of it. So they're comparing other things to Eskimos. So if Eskimos, for example, have a lot of words for snow, like 50 words for snow, then maybe British people have 1,000 words for different types of tea. Like, for example, German. So Stefan and I are both from Germany, and there's the stereotype that Germans love bureaucracy and sort of organizing things. So there's also an example which goes like, if Eskimos have 100 words for snow, then Germans have 1,000 words for bureaucracy, which might be true. I don't know. I haven't counted. So to summarize the characteristics of snow clones, they can be divided into 3 characteristics, or at least that's what we would suggest. So on the one hand, as I mentioned, snow clones usually have a lexically fixed source construction. So they are derived from an instance which is lexically fixed. That is, it consists of specific words. So in the case of the mother of all X, the original instance was probably from a speech by Saddam Hussein, who said, the mother of all battles. From this lexical source, you then introduce variation, or into this lexical source, you introduce variation, and you turn it into a more productive pattern. So the second criterion for Snowclones is that they have productive extensions, and they have this open slot. For example, the mother of all X has an open slot, like a noun, which comes at the end. And a third feature is that these constructions usually are a bit special in terms of how they are phrased. And this could be captured in terms of extravagant features. So usually there's something about these constructions which is a bit unusual. It could be unusual semantics. For example, they have really like strongly, like very intense semantics, or they could encode paradoxes, or they can encode hyperboles. There could be something syntactically strange about them. There could be something morphologically anomalous, or there could be multimodal elements in these constructions. In all of these things, we would capture with the term extravagance, as if the constructions themselves are extravagant. And we're going to say a few more words about that at the end of today's session. But for now, we want to focus mostly on the second criterion, sorry, on the productivity of Snowclones. I've had a bit of a cold recently, so okay, I hope it's okay. So yeah, before we get to that, I just mentioned that Snowclones are not the only constructions of their kind. So Snowclones are part of what we would call partially filled constructions. Why are they partially filled? Because they consist of fixed elements, like the mother of all, and then of one or several open slots that can be represented by variables. So for example, the variable X. So they are partially filled in the sense that they only have partial lexical material and then some open slot after that. Now this is sort of brings us to our first discussion question. So just in case you have some ideas, can you think of any other partially filled constructions that exist in language? So either constructions that have been investigated, you might have read about some constructions, or that would be worth investigating with the help of corpora. We were just wondering if you have some ideas about examples. We can give you some examples afterwards, but we were also wondering if you have come across something in your own reading. So if you have come across something, or if you can think of another construction, please feel free to write it in the chat now. If not, that's no problem. It also depends probably on your background. So if some of you are a bit more familiar with construction grammar talks a lot about these partially filled constructions. Whereas if you're from other traditions, maybe it's a relatively new concept to you. Does anyone have an idea? You could either write it in the chat, or you could also unmute yourself. Just gonna wait for a moment. Okay, maybe you need some more, like a bit more input from us to also trigger your own, maybe to relate it to what you've done in terms of reading before. So what could be other kinds of partially filled constructions apart from Snowclones? There's, for example, this construction, which has been discussed by Kay and Fillmore. What's X doing Y? For example, what's that fly doing in my soup? Or what's that kid playing over there? So this is a construction which is a classic in construction grammar. And as you can see, it also has fixed elements. It has the lexical elements like what's, and it has open slots. So that's why we call it a partially filled construction. Another example is the X or the Y. So this is a construction that is used to compare two things. If one thing increases, then the other thing increases as well. Sort of like the better I get at linguistics, the better I perform in my exams. Or the more workshops of corpus methods I attend, the more proficient I get at using those corpus methods in my own research. So that's another partially filled construction because it contains this lexical material, the definite article the, and it also contains open slots, X and Y. Exactly, the more the merrier would be another example of that. So that's almost like a fixed expression, but it fits into this general pattern. Another example would be go un verb en. So things like go unnoticed, or go unseen, or go unacknowledged. where again, you have an open slot for the verb, and then you combine it with a lexically fixed element. Another one which has been discussed is noun waiting to happen. So you can use any, like you can use a certain number of nouns in this construction. For example, this is an accident waiting to happen, or it seemed like an accident waiting to happen, or it seemed like a disaster waiting to happen. So it's often used with negative nouns. Another one is what is also called the into causative. For example, she talked him into helping her with her homework, or she coaxed him into, or like he coaxed her into doing something for him. So it's sort of when you have a causative effect on someone else, when your own action affects someone else. So again, we have at least one lexically fixed element here, which is the preposition into, and possibly also the inflectional ending ing. Of course, these methods can in principle also be applied to even more general constructions. So one example would be the English ditransitive construction. So things like he gave her the book, or she handed him the water. So in these constructions, you could sort of think of them, they're not partially filled, they're actually like almost completely unfilled. But what you could do in these constructions would be to just focus on one slot at a time and sort of like ignore the other slots for the moment. So you could say, you could look at which verbs can fill this construction, just focusing on one slot. And that almost is a bit like partially filled constructions, because you would only be looking at one slot at a time. And another example of this, just to use a different language as well, would be in Mandarin, where you have a locative inversion construction. So there you have a locative noun phrase, a verb, and a subject. And again, in this paper, for example, the researchers look at which verbs can occur in this construction. So they focus on one of the slots in the construction. There's a question in the chat. I'm just going to have a quick look at that. Why are the extravagant ones not snow clones? Is this because one cannot track the source back to a fully fixed string? Maybe I'm misunderstanding your question. Like, so we do argue that snow clones are extravagant. So that's one of the characteristics of snow clones. But we also argue, as you're pointing out, that they have a lexical source. So there are certain constructions, yeah, like for example, the X or the Y, at least we don't think it has a specific lexical source. So usually snow clones come from some kind of like quotation, either from a historical speech or from a film or from a book, or sometimes from like TV advertisements. So all the ones we discussed before tend to come from lexical sources. So we do think what's kind of special about snow clones is that they combine the lexical source with a certain amount of productivity and with a certain amount of extravagance. Cool, thank you very much for the question. Cool, so now we've given some more examples of these partially filled constructions. So if you're interested in constructions which aren't snow clones, but which still have these lexical elements and open slots, then you can probably also think about applying the methods that we're going to talk about today. So in terms of these methods that we're discussing today, we would suggest that the open slots of snow clones and also of other partially filled constructions can be investigated with a number of corpus-based tools. So first, what we could do if we just approach these constructions is we can obtain a quantitative overview of the data. So we could just try and start by getting an overview of the data. How could we do that? It would just be by simple means of analyzing token and type frequencies. And we're going to show in a moment just a reminder of what token and type frequencies are. Second, we can examine the semantics of the slot fillers. So of course, what's most interesting about these constructions is which words go into the open slots. For example, how flexible are these constructions? Can they just use any noun or any adjective, or are they restricted to certain semantic classes? So the other question is, how constrained are their semantics? And as I mentioned before, we want to talk about two methods today. The first set of methods is called constructional analysis. And here, the key question is which lexemes are particularly attracted to the open slots of the construction? Or in other words, which lexemes are particularly typical of the constructions? Which ones are associated with these open slots? So that's going to be one set of methods. The other method is semantic vector space analysis. So there we're going to use some mathematical tools. We're going to use vectors to analyze the semantics of these items that can go into the open slots. And we want to discuss how these open slots cluster in semantic space. So at the end of this workshop today, you should have some better idea of what these methods are doing. We're going to go through them step by step. For now, we just want to briefly talk about our data and also give an overview of the data sets that we're using. So for our Snowclones project, we are using mostly data from EN-cow. So that's corpora on the web is the cow part, and EN stands for English. They also have a few other languages available. So this is a huge web corpus. It's a web corpus which has more than 16 billion words. Which is quite helpful because we will have lots of examples of our Snowclones in this corpus. And also because it's online, it's more likely that they're quite recent examples. And especially with Snowclones, those are like quite fashionable expressions. So it's good to have a corpus which covers sort of internet slang and sort of informal internet speech, because we're more likely to find those Snowclones there. To get an overview of the data, we're going to look at two Snowclones today. So the first one is the mother of all X. And here you can see the number of tokens, types, and hapaxes that we found in the corpus. Just as a reminder, tokens are the instances of the Snowclone. So every time someone uses an example of the Snowclone, we count it as a new token. Types are every example which uses a different slot filler. So sometimes several people might say the mother of all battles. It might occur even 100 times in the corpus or 1,000 times. Then we would count that as 1,000 tokens, but we would only count it as one type. So as you can see, the number of types is lower than the tokens, but it's still pretty high. So we still have a lot of different types of the Snowclones. So 1,669 different nouns that can go into this X slot. And then finally, hapaxes or hapax legomena are types which are only attested once. So types of the Snowclones where it's only been used by one person before, at least according to the corpus. And usually constructions that are quite productive also have a lot of hapaxes, because that kind of tells us that people have tried using the Snowclone in lots of creative ways, even if it meant that they were the only people who used it in that way. So that's the mother of all X. The other one, the other Snowclone that we're going to look at is X is the new Y. As you can see, it's kind of interesting because this Snowclone has two open slots. So we can always look at the relationship between X and Y as well. The token number for this Snowclone is 3,800 and a bit more. In terms of types, you can see we can distinguish the types for combinations of X's and Y's, or only for the X's or only for the Y's. And as you can see, the types here are a bit lower because something might not be a unique X item, so it might not be a unique type on its own, but when it's combined with a different Y, then of course it becomes a new type. So that's why the combined why the types are higher for combined X and Y items. So again, you can have a look at the number of types. They seem to be quite high, and also at the number of hapaxes. Our question would sort of be, based on these token and type frequencies, what does that tell us about the productivity of the two Snowclones? So would you say that based on these values, we are talking about relatively productive patterns? Or would you say that maybe there's not so much evidence that these are actually productive Snowclones at all? How would you interpret these data? Again, if you have an idea, please post it in the chat or unmute yourself briefly. Just going to wait for a moment here. It's also just another chance to look at the data.
Hi, I think they are quite productive. Can you hear me? Yes?
Yeah, we can, yeah.
Okay, so they seem to be quite productive in actually thinking of them in Portuguese as well. I guess we do have them in Portuguese. For example, X is the new Y. The expression actually got to Portuguese. We have like preto é o novo whatever. And that would be black is the new whatever, which I guess was the initial trend because of the color being basic. And then the new basic is pink. The new basic is whatever. But we also have the mother of all X in Portuguese as well. A mãe de todos ou todas, whatever. So I guess they are so productive that they even translate onto other languages. And comparing the hapax legomena, which you mentioned, I guess people try to produce new creative uses for both of these constructions. So yes, they seem to be quite productive, at least in my interpretation. I'm just here to assist, but as people are shy, I'm just giving some insights.
Thank you. Thank you so much. Yeah, thanks for being brave as well and speaking up. And it's super interesting to hear about Brazilian Portuguese. We didn't actually check whether the Snowclones exist in Brazilian, but yeah, like I feel especially X as the new Y exists in quite a few languages by now. And as you pointed out, especially for this Snowclone, looking at the types and the hapaxes, there are really like a lot of them compared to the number of tokens. So almost 2/3 of all instances only occurred once in the corpus. So that's really seems to suggest that these Snowclones are quite productive. Conrad, yeah?
Okay, can you hear me?
Yeah, I can.
Yeah, so I have a question concerning, measuring productivity here based on these three, let's say, variables. Do you have a position on which of the three is the best indicator of productivity? Would it be the hapaxes or types or tokens?
Yeah.
I wonder what your
yeah. Good question, and maybe you also have a view on that. So I'm happy to hear that as well. I guess for us, we would probably go a step further and also calculate at least the ratios of types and tokens. So like a common measure, of course, is a type token ratio or a hapax ratio as well. So just hapaxes divided by the tokens or by the types. We would probably use several measures. Here, this was more of as an overview just to get familiar with the data. I personally don't have a strong view on which measure is the best. It also depends a bit on the overall number of tokens. So I guess we should always take into account, like when we compare different constructions, and then we use something like a type token ratio, that probably works best if the constructions have relatively similar numbers of tokens. So maybe here it would actually work quite well with these two constructions, but it's also something to take into account. Mm-hmm.
Yeah, well, I mean, if you look at these numbers here, they're all pretty high. So there is no doubt that, that the constructions here, you want to call them Snowclones, are definitely productive. But I was thinking, would it be possible to do a kind of thought experiment and imagine that the numbers were very lopsided, so that let's just say that for one of them, the number of tokens and types would be extremely high, and then there would be no hapaxes, like 0. What would that mean? That would mean that it's pretty crystallized and no new experimentation is going on, right?
Exactly, yeah.
And then what would the opposite, extreme mean if you had, high numbers in the hapaxes and in terms of types and tokens? I mean, so that would basically mean that there would be an example, one token for each type. That would also be a pretty extreme. That that leads me to think that it's the legomena that really decide, right? Or
yeah, I think often people like also place emphasis on the legomena, which is why we included them here as well. Really good points about how like those different scenarios would probably have different interpretations, which makes you think, then do speakers always try to use a different type of the Snowclone to be particularly innovative, or do they more like sort of repeat what they've heard already and like sort of stick with the instance, and that should pattern differently in the data? Stefan, do you have other views?
Yeah, maybe I can add a few things, because I've worked a bit on morphological productivity, and of course many things that go for morphological productivity can also be transferred to syntactic productivity. And of course there are these famous measures by Harald Bayen, who basically takes type frequency and this hapax-based frequency, which he calls potential productivity, and this third measure called global productivity, which basically measures hapaxes belonging to a certain pattern against all hapaxes in a corpus. And well, from my experience working with productivity, I think it's always important to take several measures into account, because one measure will always have certain problem. So for example, the apex-based measure always has the problem that it strongly depends on the sample size. So that makes it hard to compare different measure or different values of potential productivity against others. And yeah, so I think that productivity is really a multidimensional phenomenon where you have to take different measures into account. But as for Snowclones or other extravagant patterns, I actually agree with you very much that the apexes can also be seen as well, a kind of measure of creativity, in the sense that if we have a pattern that basically only yields apexes, then this would mean that it's on the one hand, of course, very productive, and on the other hand, very used in a very creative way. Although on the other hand, of course, one of our criteria for Snowclones is that it should have a more or less identifiable fixed pattern. And that would mean that if all of them were apexes, this criterion wouldn't be fulfilled because the original pattern would have been lost, and then we could debate if it's still a Snowclone or not. But yeah, that's definitely a good line of thought, I think, to take apexes as also a measure of the degree of creativity or maybe extravagance.
Okay, can I just ask you a follow-up question? Why do you think that the pattern we lost if all the attestations were apexes?
Well, maybe it wouldn't be lost, but it wouldn't be prominent anymore. Because if it's only attested once, then it would mean that it's not in any way more frequent than the others. And what we would expect is that there's one lexically fixed pattern that is relatively frequent, as, for example, the mother of all bombs, and then there are a lot of variations that in themselves are not very token frequent. But if we expect that there's basically a source phraseologism, or however you want to call it, then we would expect this one instance to be, well, probably either the most frequent one, or at least to occur more than once, I guess.
Right, so you mean the original source would be lost, Stefan, right?
Yeah.
Yeah, right. And not maybe not the templates as such. But
yeah, sorry. No, of course. Yeah, that was a bit misleading, I guess.
Yeah. Okay. Thanks a lot, Conrad.
Yeah, thank you.
There's another question in the chat. Just try. In terms of frequency, do Snowclones need to have high enough token frequency? If so, what would you consider? Yeah, sufficiently high enough. Do you want to take that, Stefan? Or?
Yeah, that's a very good question, actually, because it's also very similar to one of the basic questions of construction grammar, where one of the hotly debated question is when is a pattern frequent enough to be counted as a construction? And I think it's the same with Snowclones. So, I mean, if we take certain extensions of patterns, I don't know if there's a well, I'm just making something up. Let's say there's a popular film title like The Lord of the Rings, and then somewhere you read something like The Lord of, I don't know, the whatever, then this way of extension would be the same that is used in Snowclones, but the question is if this one instance could actually count as a Snowclone, and I think we would say that in this case it wouldn't, unless it's because that's one of our criteria, unless it's productive, and I think productive entails that there's a certain amount of different types, although I think it wouldn't make sense to really, or it would necessarily be arbitrary to define any threshold where we can speak of a productive pattern. But I think that's actually another very important issue for productivity research in general, not just regarding phraseological patterns and not just regarding Snowclones, but regarding all kinds of items. So can we define a threshold of productivity? And if so, which criteria should we define to posit such a threshold? And yeah, maybe that's something where we need more research in psycholinguistic domains, for example, because we could assume that maybe productive patterns are stored and processed differently from non-productive patterns. But I think right now all we can do is either define arbitrary thresholds or yeah, more or less follow our gut feelings, which is actually more or less what we've done with the Snowclones, or at least for the patterns that we investigated, because in those cases that we investigated, it's relatively clear that there are numerous examples, numerous types, and I think that in most of those cases we have also a relatively high share of Helbig's legomena, which speaks for a relatively high degree of extensions.
Okay, I hope that answered the question. Yeah, as Stefan outlines, of course, it always remains subject to discussion. Here we try to choose two examples where we do have a lot of types and a lot of apaxes. So there is a good argument that those would be constructions that are worth investigating as Snowclones. But there might be also less frequent Snowclones or less frequent constructions where you could argue, is that actually a productive enough pattern to justify such an analysis? But yeah, again, like it's an interesting question. Great. If there are no more questions, thanks so much for these questions and comments. That's really great. We're just going to move on. So yeah, so this has sort of been the conceptual introduction, talking a bit about the concept of Snowclones and just getting an overview of the kind of data that we're working with. So now we're going to go into the first type of slightly more intricate corpus method that we want to talk about here, which is color structural analysis. So what is color structural analysis? We're first going to talk about it a bit more generally, and then we will explain how it works and also show an example, more technical, how you can actually implement it. So color structural analysis is a family of methods, mostly developed by Stefanovic and Stefan Gries, for investigating relationships between lexical items and the constructions in which they occur. So as you can already see, the method really lends itself to these partially filled constructions, because we're talking about the types of specific lexemes that occur in the open slots of the constructions. There are several types of color structural analyses. So it's sort of a set of different methods. There are at least 3 types, and we're going to use 2 of those today, and we're just going to mention the last one. The first one is simple collexium analysis. So here the question is, which lexemes typically occur in one open slot of a construction? For example, the mother of all X has one open slot, and we're just going to have a simple collexium analysis of which lexemes fill that open slot, typically. There's another type which is called covariant collexium analysis. And that is about constructions with 2 open slots, at least 2. And here we're investigating which lexemes typically co-occur in 2 open slots of the same construction. So in a construction like X is a new Y, which pairs of X's and Y's typically co-occur together? And that's why it's called covariant, because they vary sort of depending on each other. And then there's a third type of analysis, which is distinctive collexium analysis. As the name says, here it would be about which collexiums make a construction distinctive. So this would only be relevant if you're comparing several constructions. So for example, if we're comparing 2 Snowclones which have similar meanings, and we want to know if the meanings are completely identical and if they can be used with the same kind of slot fillers, or if there are still some differences between the slot fillers, then we might do a distinctive collection analysis between the constructions. But here today, we're just focusing on each of these Snowclones on its own, because we don't really have grounds for comparing the mother of all X with X's new Y, because they have quite different meanings. So let's start with simple collection analysis and explain a bit more detail how that works. This table might look a bit scary at first, but I think we can explain it with some examples in a minute to make it clear. But basically, the idea is that in simple collection analysis, we're interested in which words typically occur in the construction. And we're contrasting two things here. On the one hand, we're contrasting a specific word which occurs in the construction to all other words which could also occur in the construction or not occur in the construction. So we're contrasting one word with all the other possible words. And at the same time, we're contrasting the construction, the specific Snowclone, with all other constructions. And if we cross these two sort of axes, we get 4 values that we want to obtain. And based on these 4 values, we can determine how much a certain lexeme is attracted to the construction. So first, we want to know how often does the specific word occur inside the construction. So frequency of word I in construction of type C. We also want to know how often do other words occur in the same construction. So this is the same Snowclone, this cell. I hope you can see my cursor. Can you? Yeah, okay, you can see my cursor.
Yes.
Okay, I'm looking at this cell here. So this is how often does every other possible word occur in the same construction. Then we have this cell, which is how often does the current word we're looking at occur in all other constructions, so outside the Snowclone. Because we would assume that a typical word, like a word that is typical for the Snowclone, occurs quite often inside the Snowclone, but not so often out or like in other constructions outside the Snowclone. And then finally, we will also want to determine how often do other words occur in other constructions. That sort of completes the table. And then the question is sort of like, do we look at all words in the corpus, or do we only look at a specific subset of words in the corpus? Often, for example, in the case of the mother of all, we just restricted this to all the nouns in the corpus. So how often do all the nouns in the corpus occur outside the Snowclone? But there could be different decisions about what number you could put into this 4th cell. So let's look at an example. This first cell would be, how often does a specific lexeme, like hangover, occur inside the construction? So what's the frequency of mother of all hangovers? This cell is, how often do other words, so that are not hangover, that's what this means, occur in the same Snowclone? So it's the sort of the remaining frequency of the Snowclone, except for this frequency. This one is, how often does the word hangover occur outside the Snowclone? And this one is, how often do all other nouns, apart from hangover, occur outside the Snowclone? And then basically what we're doing in the construction analysis is just comparing these numbers in a statistical test. And that tells us if the distribution of these frequencies is sort of what we would expect if it was just by chance, if the word just randomly occurred in the Snowclone, but it was not particularly typical of the Snowclone, or if it occurs quite frequently compared to how often it occurs in the overall corpus, and also compared to how many other words occur in the Snowclone. So we want to translate these values into some kind of association measure, which brings together all these values in one measure, which tells us about the degree of association between the lexeme and the construction. I hope that is sort of clear. We're going to show it again when Stefan goes over the code. In terms of association measures, you could use different measures for color structural analysis. 2 of the most widely used measures at the moment are the p-value of the Fisher-Yates exact test. So that's usually used for smaller samples, so maybe for a construction that doesn't have so many instances. Another one is the log likelihood ratio, G square, which is often used for larger samples. And if you're interested, there are also some papers which discuss the limitations of these measures or the potential benefits. In our case, we're using the log likelihood ratio, G square, as a measure. So this brings us to the implementation in R. Here we just want to make a quick comment. There's a package that you can use for the software R, which is called Codestructions, and that has some easy functions to use codestructional analysis in your own work. That's by Susanne Flach, and you can download it from her website. Also, there is a tutorial which actually Stefan made, which explains a lot about how codestructional analysis is used, and we just wanted to have a quick look at the tutorial, and Stefan is going to take over here and explain it himself. How would you implement codestructional analysis or simple collection analysis in R?
Okay, thank you. So the basic idea now is that we take a quick look at this tutorial, because I thought it wouldn't be a good idea to just go over the code itself, because probably different people have different degrees of experience in R. And so what I'm going to do now is just sketch very briefly what this tutorial contains, which actually uses Snowclones as a way of illustrating codestructional analysis. So I'll quickly show you the tutorial in a second and switch between the web version of the tutorial, which we see here. Just a second, I have to get rid of this bar so that I can navigate between different tabs.
I guess Tobias has to stop sharing his screen so we can see Stefan's. Okay.
Oh, thank you.
Right, sorry about that.
Okay, now you can probably see the tutorial. I'll also post the link in the chat, because that's what I'm going to briefly show now. And what we see here is so-called R Markdown document. So it's basically written in R with lots of code in it, but written in a way that you can actually read it if you want. So if you want to go into the details, you can just read the whole thing afterwards. For now, we will, however, focus on the code in here. And to show you the code, I will go to the source code in R. And as Tobias already said, we'll start with simple Codex analysis, and I'll quickly show how we implemented this. So we need several kinds of data to fill in the 4 cells of the table that Tobias just showed you, and that we also see here. I hope you can see it, where we have these different frequency values that we need, and here we see the same with a couple of examples. So if you have one lexical item, for example, hangover, we need 4 values. We need the frequency of mother of all hangovers. We need the frequency of mother of all with any other lexeme than hangover. We need a frequency of hangover in all other constructions that are not mother of all X. And then we have to fill the notorious 4th cell, which is one thing that is often discussed controversially in research on codestructional analysis, and it's sometimes also criticized that it's not entirely clear how to fill the 4th cell, because there are always different options. One very simple option would be to basically take the entire size of the corpus as the baseline for the 4th cell and basically just subtract all the values from the other cells from it. Another option would be to take for example, the word class that we are dealing with into account. So basically to take all nouns in the corpus and take them as the baseline. And that's actually what we are going to do now. Okay, and so we need, on the one hand, the attestations of the Snowclones, and on the other hand, we need the the frequency list of the lemmas in the corpus. And here we have a file that contains the mother of all data. So that's basically our concordance that we used and that we extracted from the ENCOW corpus. And as you can see, it has lots of different columns. We can also take a look at it in this viewer here. So for example, we have a couple of annotations, and most importantly for us, it's also lemmatized. So the lemmatization has been corrected manually by Tobias and me, and that's what we are going to work with. If you want to have a look at those data, then you can head to the data folder on the GitHub repository. That's also linked in the tutorial, and in the mother of all X folder, you can find the annotated data file both as CSV and as Excel table. Okay, now we have to do a bit of data wrangling, and so one idea of this tutorial is also to give you some idea about how data wrangling for color structure analysis works. This is probably too much if you haven't worked with R so far, but probably a couple of you have worked with R and know what I'm doing here, but I'll try to give you at least a sketchy impression of what I'm doing. So the first thing we do is we exclude the false hits. So there are a lot of false hits where we have things like the mother of all, I don't know, sisters or something, where actual genealogical relationships are denoted, and we first exclude them by only keeping the ones that we annotated as the ones to keep. And now I just compiled a summary table here where we see the number of tokens, number of types, and as an example, the frequency of hangover. So that's how we got our data that Tobias just presented. And we can ignore this because that's just for the HTML version in the tutorial. Okay, we can also ignore this because that's also just illustrative. And now we need the full frequencies of the lexemes in the corpus. Now, how do we get to those frequencies? Luckily, the cow corpora have this lovely section with open data, and there are full frequency lists. So for example, here we have the frequency lists for ENCOW, and they come in two versions as lemma frequency lists and word frequency lists. In our case, we take the lemma frequency list, that's this one. You can see even in the zipped version, it's pretty big. And we read it in. I've commented this out because it takes a bit of time to compute, but I'll still quickly show you how it works and uncomment it. And to read it in, I use a library called Room, which is not that well known, I think, but it's quite good actually, because it's really good for processing large files very quickly. Some of you might know Data Table, which is another well-known package for reading in large files, but actually Room is even faster. So I use it to read in this data set with the entire ENCOW data, well, not the entire data, but the frequency list. And here we can see it. So for example, the determiner is attested around 490 million or even 4 billion times. In the next step, we filter out the nouns because we only want to use the nouns, and as the cow corpus is tagged with the pen tag set. I've looked up the tags for nouns in this corpus, and now I basically calculate the sum of all nouns, which is then what will be used for filling the fourth cell. And I've also exported the rows that are in that are attested, or the rows that contain lemmas that are attested in our database. And that's what I'm going to read in now. So now this ncow object only contains the lemmas that are actually attested in our database. So in our concordance for mother of all x. And as some of the lemmas occur multiple times with different POS tags, we first have to summarize them, which I do here. And again, as an example, I take a look at the frequency of hangover, and here we see the frequency of hangover in the entire corpus. So that gives us all the values that we need. So we have the frequency of hangover, basically just illustrating again with just one example, we have the frequency of hangover in the construction. That would be what we call A here. Then we have the frequency of all other mother of all instances with lexemes other than hangover. Then we have hangover in other constructions, and then we have all other, in this case, nouns in the corpus. And if we put this in one data frame, then it looks like this. So these 4 values are needed to fill the 4 cells for calculating the construction strength of hangover. And as Tobias already said, there are a couple of different association measures that we can use. For example, the Fisher-Yates exact test, which Stefan and Chris use. We can also use the chi-squared test, which has the additional advantage that we can use this function to get the expected values as well. And so we can actually compare the observed values with the expected values, which would then look something like this. So for example, in the case of mother of all hangovers, we have 62 instances where the expected value would be 0.042 instances. So we can already see that it's that's clearly a strongly attracted colloxeme. So it occurs much more often in the construction than we would expect if we assumed a chance distribution. Okay, and of course we don't want to do this for every lexeme individually, so that was just for illustration purposes. We want to do it for the entire thing, and so we could either automatize the lines of code that I just showed you, or we can draw on the fact that luckily Susanne Flach has already done this for us and load this Colostructions package. Unlike other packages, Colostructions is not yet available on the Comprehensive R Architecture Network, or CRAN for short. So all the packages that are on CRAN you can install basically by just typing install packages and then put it and then telling the name of the package, like language R, for example, and it's automatically installed. This is not possible for Colostructions. Instead, you'll have to look it up on Susanne Flach's website and install it from there. So I can quickly show you the link again, and then you basically just have to follow the instructions there, which is relatively easy, so it's not that much more work than typing install packages. And the call instructions package has three major functions. They are collex, collex covar, and collex dist. There's also multiple covariant collex scheme analysis, which is, as the name tells you, just a variation of covariant collex scheme analysis. But we will focus on simple collex scheme analysis and covariant collex scheme analysis today. And if we want to know how to use these functions, it really helps to take a look at the documentation. So you can look at the so-called vignette by putting a question mark before the function name. And then we see here that which arguments the function takes, and this one here is most important for us because it tells us what kind of input the function takes. So in which format do we have to provide our data? And in this case, we have to feed the function with a data frame with types in a construction in column 1, construction frequencies in column 2, and corpus frequencies in column 3. So in all cases, these functions are also accompanied by example data frames. So if we, for example, load those data here, data go verb, then we see how the input should look like. So we need a data frame with 3 columns, the first one containing the word or the lexeme, the second one containing the frequency of the word within the construction, so in our case within the construction mother of all x, and then we need the corpus frequency of those words. And that's what we get by doing a couple of things. So at the moment, we have these data in different data frames. On the one hand, we have the MOA data frame, so the mother of all data frame, where we have the frequency, or from which we can obtain the frequency of the individual lemmas. And that's actually what we can, what we'll do now. So here we tabulate over the lemmas, and then we get a list of frequencies within the mother of all constructions. So we can also actually sort it in descending order to get an impression of which lexical items occur most often in the construction. So we see mother of all battles, mother of all hangovers, and so on, are very, very frequent. But of course, we want to put this into relation to the entire frequency, or to the total frequency of the individual lexemes in the corpus, and that's what we do a color structural analysis. So now we need the frequency of the individual lexemes in the corpus, and that's what we have in our second data frame, the NCOW data frame. So here we have, for example, the frequency of abomination, accelerator, and so on in the entire corpus. And we can easily merge the two tables or join the two tables using either the merge function, that would be this one, which is in the base package of R, so you don't need any packages to load it, or we use a left join, which is part of the so-called tidyverse. The tidyverse is a family of packages that I'm using quite extensively in this tutorial, and here we have this function left join, which basically says take the left of the first table and combine it with or take the table on the left in this case, our TBL1, which we just created, and combine it with the data from another table, in this case, the ENCOW data frame. And if we do that, so we have TBL1 here, so that's our anchor point, basically. That's wrong, that's the right one. Here we have a data frame with 1,669 rows, so these 10 and the 1,059 more. And if we combine them with the ENCOW data frame, we can check if everything went well by comparing the size of the data frame. So if it is more or less rows, then something's gone wrong. But in this case, it matches, and so it seems to fit. Okay, so now we have a data frame with the lemma in the first column, the frequency in the mother of all construction in the second column, and the total frequency in the corpus in the third column. And as we've seen before, that's the input that the Codex function requires. So we could just use it as input for the Codex function, but now we see that we get an error. Why do we get an error? The answer is very simple. If we take a look at this error message, and especially at the problematic rows that it gives us as a very helpful output, then we see that there are a couple of rows where the frequency value, so this frag column, which indicates the frequency in the entire corpus, where the frequency value is NA, so there is just no frequency value. Why is that the case? That's a very simple explanation for that. The explanation is that we are dealing with two different types of lemmatization. So in the data frame for the mother of all construction, we are dealing with manually annotated, or at least manually corrected lemmas. And in the case of the total corpus frequencies, the ENCOW data frame, we are dealing with automatically lemmatized data. And this means that especially in such cases where we have things like mega mover, beam prop, and all those not really frequent items, in those cases, we can expect that they have either been wrongly, wrongly lemmatized in the original data frame, or that they have not been lemmatized at all. In such cases, we often have the lemma unknown in the corpus. And of course, as we are dealing with the lemma frequency list here, it didn't enter the data frame that we were using. So what can we do here? We can just replace these NAs by 0. There's a helpful function called replace NA, which does this automatically. And if we now try Codex again, we will again get an error. Why is that the case? Well, it's the case because it wouldn't make sense to assume that, for example, one lexical item is attested twice in the mother of all X constructions, but not at all in the entire corpus, because that would mean that if we subtract the mother of all frequency, then the value to fill the second or third cell with would be -2, and a value of -2 is not very helpful in corpus linguistics. So what we can do is that we either look up the corpus frequencies manually, which would be a lot of work and wouldn't change the results much. So what we did here is that we just excluded those items, which we did using this very simple line of code, where we exclude everything where the frequency within the construction, so the frequency within the mother of all construction, is smaller than the frequency no, the other way around. We limit it to the ones where the frequency in the mother of all construction is either smaller than or bigger or as big as the frequency in the corpus. And now we can use the Codex function again. And in this case, it works. And here we get the results. And for taking a closer look at the results, we will switch back to the presentation in a minute and take a closer semantic look at them. But before we do so, let me just take the opportunity to ask if there are any questions at this point. I'll stop my screen share for a minute so that I can see you all and see if there are questions. Okay, so I hope I haven't overwhelmed you too much, and I give back to Tobias for a second.
Okay, thank you, Stefan. I think you just explained it so well, so there weren't any questions. Or maybe we will have some questions later on. That would obviously also be totally fine. I definitely learned a few things from your tutorial, even just like the abbreviation for CRAN, what that actually means. So that was good to know. But yeah, we hope that that was sort of a guide by which you could actually maybe go back to Stefan's website and look at his code and then actually use that code or parts of it in your own research, because it's all open source and available, right, Stefan? Yeah, okay, cool, perfect. So here we just wanted to go back sort of just to the outcome of this analysis and discuss a bit how do we interpret these kind of results from color structural analysis. So we're taking a step back from the more technical bits and going again like to the more conceptual question: what does it actually tell us about the snow clone? So here we see the results of a simple collection analysis for the mother of all x. And as you can see, according to these results, battle is number one in this table. So what do the columns of this table tell us? The first column is the frequency of battle in the snow clone. The second is the frequency of battle in the entire corpus. So that's called total frequency here. And then we get the critical value from our color structural analysis. So the color structure strength. And we don't need to worry so much about how high exactly the value is. Mostly we can just look at the relative size of the values. So here we see that battle has a very high color structure strength. And the final column tells us how significant that result is. So is that statistically significant? Here in this table, we're just focusing on the 10 topmost instances. So the ones that are most strongly attracted to the construction. And as you can see, they are all very significant, the values. And the color structure strengths are quite high overall. Still, we can of course look at certain like relative differences between these color structure strengths. And for example, this tells us that battle, according to these data, is the most strongly attracted colexeme of the construction. That's of course quite interesting because we assume that the construction derives from the lexical source, from the speech by Saddam Hussein, where he used the construction with battle. And it seems like quite a lot of people have used the construction again in this original version. And then we see the other lexemes that have been used since then. And we can, for example, see that hangover, bubble, and crisis, and the other words here are very typical words in the construction. So they occur much more frequently in the construction than we would expect if words were just randomly inserted into this construction from the corpus. So our brief question here is, looking over these words, would you say that they have anything in common semantically? And if so, what does that tell us about the semantics of the snow clone? So if you have any idea, again, please use the chat or unmute yourself. Is there something which is semantically sort of a commonality here? Negative meaning, someone wrote, yeah, thank you. Marcia, exactly, that's definitely striking. Negative meaning, battle, of course, is negative sort of in the original instance. And then we have words like hangover, which is quite a negative state to be in. And we also have things like crisis or bubble, which is often a financial bubble. We have headache, which is quite similar to hangover. We have just like sort of words like cock up here, which is like a colloquial word to describe a negative situation. Adventure is maybe a bit more positive or neutral, but then again, something like bomb or even storm are often quite negatively connotated. Right, so that will be one commonality. Is there anything else? Any other ideas? Okay, maybe not for now. So let's just focus on how we would interpret these results. And this is sort of just a qualitative interpretation based on the most strongly attracted collectemes. So we use a quantitative measure to arrive at the collectemes, and then we can have a qualitative look at their semantics. So we have quite a lot of abstract nouns with negative connotation. So not only are they negative, but they're also quite general often. So abstract nouns like bubble or crisis or bailout. We also have a number of everyday concepts. So we both have abstract concepts and more like everyday concepts, like, well, which are still in the abstract realm. So we have things like traffic jam or hangover or headache. And also we can note that we have quite a lot of colloquial usage, which probably indicates in what context this snow clone is used. So there are several of these colloquial words in the most frequent collectemes, not just the 10 collectemes that we showed, but we also looked a bit further at the maybe top 20 or top 30 collectemes. So, and then like just as a reminder, battle seems to be the most typical instance. So that gives us some credibility or some support for this hypothesis that the snow clone, or that the original instance of the snow clone is still quite, that speakers are still quite aware of that original instance, and that they are sort of using that as a model to then extend the snow clone to other patterns. And what we can do now is, of course, do the same with the X is the new Y snow clone. So our second example. Here, we are not going to go through the whole code, because you could basically use the same code, of course, with certain adaptations for the data, but you could use the same functions and apply it to other snow clones like this one. For the simple collection analysis, we're just focusing on one slot at a time. So here we're going to first look at the simple collectemes that typically go into the X slot of the snow clone, and then we're going to look at the ones in the Y slot. So what are the ones in the X slot of X is the new Y? Here you've got the collection table. So here we've got green, pink, black, small, gray, white, gray, blog, and transparency. As you can see, 7 of those are colors. So that's definitely one really strongly represented category. Apart from that, we have sort of blog and transparency, which are maybe related to online media. So you can also see that this term, this construction is often used to describe things in the online modality. We couldn't show more collections here, so we're just gonna, so when we draw our conclusions, we would base this on a slightly larger selection of collections, not just on the 10 most attracted ones, but this is just sort of an example. In the Y slot of the construction, we have some more variation. So in the for the Y collectemes, we have black, sexy, oil, Nazi, big, pink, cupcake, the Ku Klux Klan, and objectivity. So what you can see here is that black is sort of the most representative color. And that was also mentioned, I think, by Gabriel before, that it's almost like the snow clone might have a sub pattern which always has black in the Y slot. Because if you look at the frequency of the inner construction and also construction strength, these values are really high. So in more than 600 instances of the snow clone, we have a pattern of X is the new black. Apart from that, we also have a few other adjectives like sexy and big, but we also have group terms, so group membership terms, sometimes negatively connotated, like here with Nazis or the KKK. We also have some other group membership terms that appear. And then we have a few other types of lexemes. We have sort of concrete objects like cupcake, but we also have more abstract terms like objectivity. So this seems to suggest that the snow clone is a bit more flexible with respect to the lexemes that it accepts or that are typical. So in terms of interpretation, slot fillers instantiate a variety of semantic classes, colors, groups, abstract concepts, concrete objects, etc. Of course, colors were quite were quite representative, or were quite frequent in the snow clone. It's interesting to know that a range of colors are tested in the X slot, but in the Y slot, black is by far the most common color. So again, that could indicate that there's a possible subconstruction, which is just sort of a more limited pattern, just X is the new black. And maybe that's also how the snow clone developed, sort of by first taking that more lexically fixed pattern and then making it more general over time, even though that's just a hypothesis for now, because we don't really have the kind of diachronic data to test that, at least at the moment. Oh yeah, okay, sure, no worries. What's of course interesting is that now we've only looked at each slot separately. We've only looked at which lexemes go into the X slot and which ones go into the Y slot. We haven't looked at how are X and Y actually combined in the snow clone. Like, what is the relationship between the X lexeme and the Y lexeme in one specific instance, or in every other instance of the snow clone? So in order to test this, we can't just use simple colexeme analysis, but we need to use covariant colexeme analysis. And that's what we're going to discuss next, just briefly. So for covariant colexeme analysis, we're just changing our table a bit. It still looks complicated, but we have slightly different things in this table now. So if you think about it, before in the simple colexeme analysis, we compared how often a word appears in the construction or in the entire corpus. Whereas now we want to compare how often a specific word appears in one slot of the construction against the other slot of the construction. And that changes our cells in this table. So here, these two sort of heading, like cells in the header, are one specific word in the first slot of the construction, and then other words in the same slot, in slot 1 of the construction. Whereas here we have any word in the second slot of the construction compared to any other word that appears in the second slot of the construction. And if we cross over these things, again, we need full values for our analysis. We need basically the values that I just explained. So frequency of one word in the first slot of the construction, frequency of any other word in that first slot of the construction, frequency of other words in this of the word in the second slot of the construction. Oh, am I confusing things here? Stefan, can you help me for a sec?
Maybe it helps to use the example of the
okay, let's use the example. Yeah, okay. Right. So in this first cell, we're just looking at an example like pink is the new black. We're comparing that to, okay, yeah, the example does make it clearer, to a case where we use any other lexeme in the first slot, but we keep the lexeme in the second slot. So any other thing in the first slot, which is not pink, but which is still combined with black. Then we look at how often pink in the first slot is combined with any other lexeme in the second slot. And finally, we look at how often any other lexeme in the first slot is combined with any other lexeme in the second slot. So I hope I got that right now. Of course, it's interesting, this is all inside the construction. So here we're not looking at how often these lexemes occur outside the construction in the rest of the corpus. Again, this is also included in the tutorial that Stefan has. So that will be the next chapter in the tutorial. Do you want to go over it, Stefan? What do you think?
I can quickly show it. It's very brief because it's we basically stay within one construction. So all we have to do is okay, here I'm reading in our concordance again. So as you can see, we have lots of variables in this case because we have lots of annotations that we most of them are automatic annotations that we drew from the corpus, but we also added some manual annotations which we won't talk about today, but we actually manually annotated different concepts and so on to get an impression of which concepts combine with which other concepts. But as for the covariant colexeme analysis, all we need is basically the lemma column or basically the two lemma columns, one with the X column lemmas and one with the Y lemmas. And if we have these two columns, we can just pass this to this Codex covar function, which takes as input either a raw data frame with like the one we have here, or we could also provide it with a frequency table, as we did with the simple Codex analysis. So let's just take a look at how the input looks like that we provide to the function now. So it's just a list of lemmas occurring together, and if we pass this to the Codex covar function, we immediately get our results, and yeah, we can take a look at them again in the presentation.
Okay, thank you, Stefan. All right, so as you can see, I guess once you've set up the data in the right way, it's actually quite easy to run these functions in the end. So what the covariant collection analysis tells us is how often certain combinations of x's and y's occur together in the snow clone, compared to a situation where we would just take all the words that occur in the snow clone and just randomly pair them together. But we want to see how much the data diverge from that kind of randomness. So here are the results of the covariant collection analysis. As you can see, the table also has a few more columns. We have collection 1 in the first slot and collection 2 in the second slot. We have the frequencies for both collections, and we have the combined frequency, so how often they occur together. For example, for small and big, you can see that small occurs 77 times on its own in the snow clone. Big occurs 75 times in the Y slot of the snow clone, but also they can occur 75 times together in the snow clone. So that actually means that whenever big is in the Y slot, then the X slot is always small. And it's almost the same for the other way around for small and the X slot. So that gives us a very strong construction strength, which means that this pairing is particularly typical in the snow clone. So if we look at the 10 most typical covariant collections, we can make a few observations. One particularly interesting observation is maybe to look at the relationship between the two words in X and Y, and seeing that they often express quite a big contrast, or they might actually be complete opposites. So small and big, for example, are opposites, or we have old and new. So this would be old is the new, which also expresses sort of that the concept of old can in certain contexts replace the concept of new, at least if you view it from like an innovative perspective. Or strong is the new skinny, or quiet is the new loud. So you have quite a few of these contrasting items here in X and Y. And then you have a few other things. You have some instances where maybe more similar concepts replace each other, like transparency replaces objectivity. Transparency is a new objectivity. Maybe those concepts are a bit more related. And then you have concepts where sort of one domain, like data, is compared to a domain which is not the opposite domain, but it's still quite a different domain, like oil. For example, here data are the new oil, or data is the new oil. So here you're comparing like a relatively abstract concept of data to a relatively concrete concept of oil. So just qualitatively, we're just focusing on one possible interpretation or observation here, which is that X and Y are often opposites, like small is the new big or old is the new, but still from the same semantic domain. But of course, what the limitation of this method is, and this sort of like brings us to the second half of the tutorial, is the constructional analysis only tells us about typical lexemes. It doesn't exactly tell us about the semantics of these lexemes. So we could see that when we get these collection tables, we still need to interpret qualitatively what these words have in common with each other, or what the typical semantics of them are. And that's sort of all the analyses that we've done so far. So it helps us to get an idea of typical lexemes, but it doesn't give us some measure of the semantics of those lexemes themselves. So the question is, could we go a step further even? Is there a way to investigate the semantics of the slot fillers, not just the types of lexemes, but really their semantics in some kind of quantitative way, and also in a bottom-up way? So could we just use the data themselves and somehow generate the semantics from that or extract the semantics. And this brings us to our second method that we want to talk about. We've still got about 40 minutes or a bit more left. So that should be enough to go through this. These are semantic vector space models, and it's going to be Stefan who's going to explain that to you. So I'm going to pass over again.
Okay, I'll quickly share the slides again and try to walk you through semantic vector space analysis. Many of you will probably have heard of this method. Maybe you've even used it. There's quite a nice introduction in the textbook by Natalia Levshina. So there's one chapter on semantic vector spaces that's really accessible. And in our hands-on part, we will actually largely follow this, this part. Okay. Yeah, I guess we'll manage that time-wise. So the idea is that as Firth famously put it, that you shall know the words by the you shall know a word by the company it keeps, and the idea is that similar words occur in similar contexts, and so given the assumption that words that occur in similar contexts have similar meanings, we get to the idea of distributional semantics. So, for example, we could compare these three corpus instances of drink and sip, and there are a couple of overlaps which show that drink and sip are relatively close together in meaning. Whereas in other cases, if we had drink and eat, for example, then we would have different collocates probably. So semantic vector space models compute semantic vectors which represent the meanings of words based on their context. So they basically take words in their context and transform them, as it were, to vectors, and based on similarities between those vectors or dissimilarities, they try to quantify how close to each other or how distinct different words are. And following Levshina, we can do a semantic vector space analysis in 3 steps. In the first step, we create semantic vectors from word co-occurrences. In the second step, we compute similarity scores between vectors. And in the third step, we explore similarity scores. And we'll briefly go through these different steps. So the first step would be to create semantic vectors. If we take the mother of all x as an example again, then the first thing we would have to do is create a co-occurrence table. So how often does each collocate occur within 5 words to the left or 5 words to the right of the slot filler in the corpus. So what we do is basically, if we have let's take hangover again. If we have hangover and we want to get the collocates of hangover, then we take the examples in our data set, but we also go beyond it. So we take all instances of hangover in the corpus, and we take the 5 words to the left and the 5 words to the right, and create a frequency table, or a so-called term matrix. So I'll quickly share a link where you can read a bit more about this if you want, because actually in the hands-on part we won't do these matrices, but there's this very a nice book about tidy text mining, which also introduces the R packages, the R package tidy text, which can be used to create such document term matrices, and there you can get some clues on how to create such frequency tables. So the first step would be to create such coherence tables. So if we have hangover, for example, we have lots and lots of collocates. Here we only see the few that are alphabetically first, and we see, okay, after occurs 3 times in the context of hangover, asked occurs twice in the context, and by context I mean 5 words before and 5 words after. And then,
sorry, Stefan, I can't see your slides anymore. Maybe it's just me, but
thanks. Oh,
okay.
Yeah, maybe I just, sorry, I actually didn't share them. I only put them to full screen, but that doesn't help you, of course. Okay, now you should be able to see them again.
Thank you. Yeah, I saw them before. They were just gone for a moment.
Okay, thank you. And then we basically, from these frequencies, we calculate positive pointwise mutual information scores. Positive pointwise mutual information is, well, as the name says, a mutual information score that basically checks which, in a very simple way, how much information 2 words share, so that more surprising co-occurrences are given more prominence. And this in turn gives us a series of vectors with PPMI scores. We will do this in a second. And in the second step, we compute similarity or distance scores. So the semantic vectors are compared with the help of a similarity measure. In this case, we take cosine similarities, which basically computes the angle between the vectors. So if we transform the vectors to geometric shapes in a way, or to 2 lines, then the angle between the vectors indicates the distance between them. And by subtracting the similarity scores from 1, we can also obtain distance scores. And in the third step, we explore similarity scores by plotting them, for example, in a diagram according to how similar they are. And in this way, we can also identify clusters of similar units, either manually or automatically with algorithms such as partitioning around medioids or other automatic clustering algorithms. So in our supplementary material for a paper that we recently submitted, we did this for x in y, and we also did it for mother of all x, but that's not in the GitHub repository, that's in this OSF repository. So if you want to take a look at the code that I'm going to show you in a second, you would have to go to the OSF repository here. I'll copy and paste the link to the chat, and there you find the data and the code. And I'll head over to R again, and here we see the code for the distributional semantics analysis of mother of all. And as I said, I skip the part where we compile the frequency lists of the collocates because that takes a lot of time. And instead, I read it in immediately. So here we have all the keywords with their collocates. So the first 5 and the last 5 words in the context, which we extracted, in this case, from the Corpus of Contemporary American English, COCA. And in the first step, we combine these 2 columns with the last 5 and the first 5 words in the context to one single column. And now we have one column in which both are basically pasted together, as we can see here. So the order of the words doesn't matter because we're just interested in the words that occur in the context. And now we remove all the contexts that we don't need. So we just need the keyword column and the combined collocates column. And then we use the unnested tokens function from the tidy text package, which is the package which I just showed you and which is treated in the book that I pasted in the chat. And doing so, we get this frequency table that I called DTBL. And in the next step, we let's just take a quick look at how it looks like. Okay, so here we just have the keywords and the collocates now each in one individual row. And from this list, we can make a table, which we then transform to a data frame. And now we can get the point-wise mutual information. And to get the point-wise mutual information, we can take the expected values from the chi-squared test and then use this formula to calculate the PMI score. And in the next step, we calculate the positive point-wise mutual information score. So positive point-wise mutual information is basically a variation of point-wise mutual information, which assigns more prominence to the more surprising elements. So the difference between PPMI and PMI is that in PPMI, as you can see here, if the value is below 0, then it is basically corrected to 0, and in this way we get those PPMI scores, which basically looks like this. So you can't read very much because the row names and column names cover everything, but under the hood, it's basically just a matrix of PPMI scores. And in the next steps, we basically follow the things that Lefschner does. Actually, Lefschner also has a package that does the same thing. So she's compiled an entire R package that accompanies her book. But in this case, to illustrate it in a bit more detail, I've basically just extracted the relevant lines of code from the functions so that I can demonstrate the basic ideas. So here we calculate, here we basically compile a table in which we then have the PPMI scores together with the different lemmas, and in this way we get the cosine distance using this cross product function that we see here, and that's rather complex. But if you break it down into its individual functions, it's actually quite easy. And doing that would take a lot of time. So instead of doing that, I'll read in the file that I saved. So I basically executed this code and exported the result. And this is how the result looks like. So what we see here are the cosine distances between different words. So if we take a look at this here, for example, we can see the cosine distance between, let's say, alignment and overdose, or between alkaloid and parade. And using this input, we can now calculate the distances between them. So before that, we had the similarities, and by subtracting the similarities from one, we get the distances. Now I make a backup copy in case we need this later on. And I use the sdist function to transform it into a so-called dist object, which is a certain object in R that can then be used to as input, for example, for the CMD scale function, which is a function for multidimensional scaling, which is a popular way of dimensionality reduction. So if you have data with various dimensions and want to break it down into 2 or 3 dimensions, then you can use multidimensional scaling, and that's what this CMD scale function does. And we apply this to our matrix now. And we transform the row names to columns and add the column names. And then we can also use an automatic clustering algorithm if we want, and define how many clusters we want. In this case, I went for 20, which is probably a bit much, but for expository purposes, that doesn't matter. What we can also do, if you want to read about this, that's also discussed in much detail in Lefschner's book, we can use this silhouette width to compare different different numbers of clusters, but I will skip this and instead just show the results, because one of the things that we of course want to do is we want to plot the results, and that's what we are doing here. So by doing multidimensional scaling, we basically told R that the items that are close to each other by in terms of their semantic distance as computed by the cosine distance should be plotted close to each other, and those that are more distant should be plotted in a bigger distance. And so what we see here, for example, I hope you can see the pop-up window as well with the plot. Because if you can, then you should see that there are, for example, sauce, recipe, pork and pizza and egg and jam close to each other, and many more. So that's quite comforting because those seem relatively close to each other semantically, and they are also plotted close to each other. So it was really a very quick walkthrough, and probably too quick to really follow, but I hope that I could give you a quick impression of how this could work. And if you want to take a closer look at it, as I said, you can take a look at the OSF repository where the data is available, and also in Lefschner's book where these individual steps are described in much more detail. Okay, and I think I'll give the floor back to Tobias.
All right, thank you. Do you think we should sort of wrap up, or what is the plan? Yeah.
I think so, at least in the comments, it's that we should take the last 30 minutes for discussion.
I guess,
so.
yeah, I mean, yeah, true. Well, we did start the discussion a bit sooner, like sort of at the start of the course. So I think that's fine, maybe. I'll just like wrap up then with like some final comments. So this was sort of our last part. So we discussed several methods today in the workshop. We discussed color structural analysis and both simple and covariant collection analysis. And then we also went into semantic vector space analysis, where you could sort of use these mathematical tools to compute vectors, then derive semantic similarity values, and then look at where the slot fillers in the Snowclone cluster in semantic space, and sort of identify these clusters that Stefan outlined. So at the end, we just wanted to like summarize sort of like a few points about what these methods can tell us about snow clones. And of course, also with the view, again, that these methods could also be applied to other partially filled constructions. So any construction which has open slots, and then like a variety of lexemes which fill them. So of course, the first issue we kind of talked about today was productivity. So these methods can be used to sort of gauge how broad or constrained the constructional semantics are of a construction, at least as a sort of like one of the components that go into productivity. So productivity is maybe not just the frequency of a construction, but it's also how much of semantic space it covers. If a construction can combine with lots of different semantic domains, it's probably more productive. And these methods give us sort of a bit of a window into these semantic judgments, which are otherwise quite hard to make sometimes. Sort of following up from this, apart from productivity, the methods also tell us something about the semantic profiles themselves. So which semantic domains does the specific construction prefer? Does it focus more on colors? Does it focus on abstract terms, on concrete concepts? In construction with two slots, do we have quite a big distance between the elements in the X slot and the Y slot semantically, or are they often quite similar to each other? Those are sort of questions that we could address with these methods. They might also at least provide us with some indirect evidence of potential subconstructions. So we saw in the X is the new Y example that some slot fillers seem to be so frequent, and not just actually frequent, but also so typical of the construction, that they might be regarded as productive subconstructions in their own right. And we could probably run some follow-up analysis to look into this further. For example, we could just do another maybe constructional or semantic space analysis of just the pattern X is the new black to see sort of the semantic space that this subpattern covers, and then see if, and then we could have a discussion about whether that justifies saying that this is a subconstruction of the more general X is the Y pattern. And finally, coming back to these extravagant characteristics that we mentioned at the beginning. So we also saw in our analysis some results which suggested that these snow clones do have some kind of special stylistic characteristics. And we can use the semantic information we obtain from the methods to maybe give some to give us some idea of what these characteristics consist in. So for the mother of all X, for example, we could say that it often seems to be used to characterize quite negatively connotated concepts in quite a strong or exaggerated way. So if you think about it, concepts like crisis or screw up or these kind of emotionally connotated concepts, they are quite strongly connotated in themselves. So if you combine them with the snow clone, if you say it's the mother of all crises, then you're sort of really highlighting that that kind of connotation. And we can maybe, and we get some, we find some evidence of this semantic extravagance by looking at the typical collocates and at the typical semantics of the construction. Whereas for X is the new Y, we could, for example, argue that the extravagance of the construction is due to the fact that it often makes these innovative comparisons between X and Y concepts, which are actually quite different from each other. So this construction is often used to draw innovative comparisons between two seemingly incompatible concepts. Like, it's not quite obvious why small should be the new big. So the speakers try to be almost intentionally provocative when they combine contrasting terms and compare them to each other. Or when you say things like statistics is the new grammar, you really have to have some like knowledge of the context, like maybe it's in linguistic context, why it would make sense to talk about statistics in terms of grammar, because technically those concepts don't seem to have so much in common. So again, by analyzing the semantics of each slot and also comparing the distance, the semantic distance between X and Y elements, we could obtain some measure of how innovative these comparisons are. And thus we could talk about the typical semantics or the extravagant semantics of the construction. Of course, some questions still remain, sort of how we could actually quantify such extravagance. So far, it's kind of still like a qualitative analysis. We obtain some quantitative measures, but then we still need to interpret them in certain ways. But that's also an area for future research that we're quite interested in. Sort of how can we determine from corpus-based measures how innovative these constructions are, or how creative they are. And if you have any thoughts on this in the final 10 or 15 minutes, we'd be very happy to hear them. So just for now, that's it from us for today. I hope you enjoyed it. I hope we were able to cover different aspects, conceptual and sort of more technical. And we'd be happy to take any more questions, or if you have comments on our project, that would also be great.